In this video, we're going to look at other examples of aromatic heterocycles than pyridine and pyrrole, and talk a little bit about the aromatic stabilization energy of aromatic heterocycles, answering the question, how does that compare to the aromatic stabilization energy of benzene? Are these molecules more or less stable than benzene in general terms is the question we're asking here. First, let's take a look at some other types of heterocycles. So we've got both 5 and 6-membered heterocycles here on the slide. Important 5-membered rings containing oxygen and sulfur respectively are furan and thiophene, and we see the O2 and S2 atoms in these aromatic heterocycles. Very similar to pyrrole, actually, conceptually speaking. Pyrimidine and pyrazine are like pyridine, where another one of the carbons has been replaced with an N2 nitrogen. So these azenes, as they're called, abound in N2 nitrogens. And pyrazine is actually important in cooking. It's been found in as a product of Maillard reactions, for example, when you're cooking and charring food. Azoles are characterized by an N2 nitrogen together with another heteroatom. So for example, in each of these, in imidazole, we have an N2 nitrogen with an N3 nitrogen, an oxazole, an N2 nitrogen with an O2, thiazole, an N2 nitrogen with an S2. And so we have N2 nitrogens in all of these with some other heteroatom. And here I'll just pause and say that it's not really important to memorize these structures per se. I just want to try to train you to get in the habit of looking at the bonding patterns of the heteroatoms when you encounter an aromatic heterocycle. This is going to get you thinking about things like basicity and is that lone pair part of the pi system? Questions like this. Heterocycles can also be fused with each other or with benzene rings. Fusing with benzene rings is very common. For example, here we have 5 examples of fused heterocycles with benzene, and the fusing bonds are highlighted in purple. When pyrrole is fused to a benzene, that's the indole structure. When furan is fused to a benzene, that's benzofuran. This can actually happen 2 different ways with both pyrrole and furan. The way you see here with the heteroatom directly connected to the benzene ring is the much more stable arrangement for reasons we probably won't be able to get into, but are worth thinking about. Try drawing the alternative isomers where the pyrrole and furan rings are fused in a different way, and think about why these might be less stable than indole and benzofuran. Quinoline has a pyridine ring fused to a benzene. Isoquinoline is also a pyridine ring fused to a benzene, but at the meta and para positions rather than the ortho and meta positions as we see in quinoline. And then benzothiophene is actually quite similar to indole and benzofuran. It's just a thiophene ring fused to a benzene ring. So these are other examples of aromatic heterocycles. Aromatic stabilization energies of heterocycles tend to be lower for heteroarenes than benzene. These heteroaromatics are a little bit less stable and a little bit more prone to react than benzene in most cases. So heteroarenes are often more reactive with either nucleophiles or electrophiles. For these electron-poor rings like pyridine, that's going to be more reactive with nucleophiles than benzene. And these electron-rich rings like pyrrole are going to be more reactive with electrophiles. So as an example of this, as we've seen, if you just take benzene and hit it with Br2, no reaction occurs. But if you try the same thing with pyrrole, you hit pyrrole with Br2, now the electrophilic substitution reaction that takes place, which we'll talk about in detail later in the course, occurs very, very rapidly, and all 4 of these H's very quickly get substituted with bromine atoms to produce tetrabromo pyrrole. So this is a very fast process because this is a very electron-rich ring. Br2 is an electrophile. When the ring is acting as a nucleophile and it's electron-rich, it's going to react very rapidly. And pyrrole, as we've already seen, is quite an electron-rich ring. So the lower aromatic stabilization energies have something to do with this as well, right? That these molecules are, in a sense, intrinsically a little bit less stable than benzene. That's why they have a little bit lower aromatic stabilization energies.